Look up at the night sky on a clear evening. Away from city lights standing beneath the stars, you see something that has captivated humanity for thousands of years. Thousands of brilliant points scattered across infinite darkness. The Milky Way stretching overhead like a river of light. Ancient civilizations built entire religions around this view. Poets wrote sonnets. Scientists dedicated their lives to understanding it. But what if everything you see up there, that entire breathtaking panorama, represents almost nothing? Not a small fraction, not even 1%, but essentially zero. When you stand beneath that perfect night sky with nothing but your eyes, no telescope, no binoculars, just naked human vision, you can see approximately 9,000 stars. That number changes slightly depending on where you're standing and how dark your sky is, but 9,000 is the absolute maximum for human eyesight under the most ideal conditions possible. 9,000 stars scattered across the entire dome of the heaven above you. Now, here comes the part that changes everything. The Milky Way galaxy, our home in the cosmos, contains somewhere between 100 billion and 400 billion stars. Even using the most conservative estimate, we're talking about 100 billion stars in our galaxy alone. You can see 9,000 of them. What you see with your own eyes represents roughly 200 thousandths of 1% of our own galaxy. Not 2%, not even a fraction of 1%. 200 thousandths. The most spectacular night sky you have ever witnessed shows you an almost unmeasurably tiny slice of just the Milky Way. Not the entire universe, not even a meaningful sample of nearby space, just our single galaxy. Every constellation you learned as a child, every star you wished upon, every meteor you watched streak across the summer sky, all of it combined represents a sample so microscopically small that it barely qualifies as a sample at all. You're looking at the cosmic equivalent of examining a single drop of ocean water and thinking you understand the Pacific. This is not just a failure of human eyesight, this is something far more profound. The night sky is not showing you a representative sample of the universe. It's not even showing you a biased sample. It's showing you almost nothing at all. The darkness between the stars is not empty space. It's not a void waiting to be filled. That darkness is packed with galaxies, billions upon billions of them, so distant and so faint that their light never reaches your eyes with enough intensity to register. The blackness you see is not absence, it's limitation. Your limitation, the limitation of biology and distance and the fundamental physics of light travelling across expanding space. But the scale gets worse, much worse. The observable universe spans approximately 93 billion light-years across. Notice that word carefully, observable, not observed. Observable means theoretically detectable if we had perfect instruments and unlimited time. Observed means we actually pointed our telescopes there, collected the light, measured the data, and catalogued what we found. The difference between those two words represents almost everything that exists. Astronomers estimate there are roughly 2 trillion galaxies in the observable universe, 2 trillion separate island universes, each one containing anywhere from millions to trillions of stars. Some are massive spirals like our Milky Way. Others are dwarf galaxies barely holding themselves together. Some are elliptical giants that devoured dozens of smaller galaxies over billions of years. Each one is a cosmic city unto itself. When you multiply all those galaxies by all their stars, you get a number that breaks human comprehension. 200 billion trillion stars. That's the current estimate for the total number of stars in the observable universe. There are more stars in the universe than grains of sand on every beach on Earth. More stars than seconds have passed since our planet formed 4.5 billion years ago. More stars than breaths taken by every human who has ever lived. And you can see 9,000 of them. Every patch of seemingly empty sky contains galaxies. If you could see in infrared, if your eyes were 1,000,000 times more sensitive, if you could stare at one spot for days and collect every photon that arrived, that darkness would explode into light. In 1995, astronomers pointed the Hubble Space Telescope at a tiny region of blank sky near the Big Dipper. The area was so small you could cover it with a grain of sand held at arm's length. They kept the telescope pointed there for 10 days straight, gathering light. That tiny empty patch revealed 3,000 galaxies, 3,000 entire galaxies in a spot smaller than a sand grain seen from across the room. Extrapolate that across the whole sky. Multiply it by every apparently empty patch of darkness you see above you. The universe is not sparse. It's not mostly empty with occasional islands of matter scattered throughout. It's dense, packed with structure, overflowing with galaxies and stars, but separated by such enormous distances that light itself takes billions of years to cross the gulfs between them. Your perception of reality is catastrophically wrong. The mental model you build from looking up at the stars bears almost no resemblance to what actually exists out there. You think you see the universe when you see the Milky Way. You think you understand cosmic scale when you imagine billions of galaxies. You think you grasp infinity when you contemplate all those stars, but you're seeing essentially nothing. Most of the universe remains invisible to you, not because it doesn't exist, not because it's hidden or forbidden, but because the distances are so vast, the light is so faint, and our instruments have only just begun to scratch the surface of what is really out there. We have built our entire understanding of cosmology, of galaxy formation, of star birth and death, of dark matter and dark energy, from studying that tiny visible fraction. From 9,000 visible stars and a few million catalogued galaxies out of 2 trillion, we constructed theories about the origin and fate of everything. We mapped the shape of space-time. We calculated the age of the universe. We predicted its ultimate destiny. What happens when we finally see the rest? What changes when the invisible becomes visible? How many of our theories will survive contact with the full reality we've been missing all along? That question should neither terrify nor excite you just now. Just let it settle there, quietly, as you rest. Because the universe we haven't yet seen is not just more of the same. It's not simply additional copies of what we already know. The unseen universe is patient. It has waited this long. It can wait a little longer while we slowly, carefully, try to understand what those 9,000 points of light are really telling us about everything else that exists beyond them in that vast and patient darkness. Galaxies, those cosmic cities we mentioned, are where our story truly begins. Galaxies are the building blocks of the universe. They're not just collections of stars scattered randomly through space. They're vast, gravitationally bound systems containing stars, gas, dust, dark matter, and often supermassive black holes at their centres. Everything we understand about cosmic structure, about how the universe evolved from the Big Bang to today, depends on studying galaxies. They are the fundamental units of cosmic architecture, the chapters in the story of everything that exists. Current estimates place the total number of galaxies in the observable universe at approximately 2 trillion. 2 trillion separate cosmic cities, each one a complete world unto itself. Some contain only a few million stars, others hold trillions. Some are actively forming new stars at ferocious rates, their spiral arms glowing with the blue light of young suns. Others are dead, their star formation shut down billions of years ago, leaving only the red glow of ancient stars slowly fading into darkness. Each galaxy has its own history, its own story of birth and evolution, and perhaps eventual death. Now, here's the devastating fact, though devastating might be too strong a word for something so quietly profound. As of now, astronomers have catalogued only 10 to 50 million galaxies in any meaningful detail. Let that number sink in for a moment. Let it settle. 10 to 50 million galaxies studied out of 2 trillion that exist. Even if we use the higher estimate of 50 million, we're talking about roughly 2.5 thousandths of 1% of all galaxies. For every single galaxy we have examined, studied, measured and catalogued, approximately 40,000 galaxies remain completely unseen. 40,000. Not 4, not 40. 40,000 galaxies for every one we know anything about. Imagine walking into a library containing 1 million books. You want to understand what knowledge that library contains, what stories it holds, what information is preserved within those pages. So you randomly select 25 books, read them cover to cover, and then claim you understand the entire library. That's essentially what we've done with galaxies. We've read 25 books and declared we understand a 1 million book collection. And the quiet truth is, we know it. Astronomers know it. They work with this limitation every single day, building theories on foundations they understand are incomplete. But the situation is actually more complicated than that analogy suggests, because the galaxies we've studied are not a random sample. They're heavily biased towards certain types. We study the galaxies we can see most easily. The bright ones, the large ones, the ones that emit strongly in wavelengths, our telescopes are designed to detect. Faint galaxies, small galaxies, galaxies that emit most of their light in wavelengths we're not monitoring. These remain invisible to our surveys. Most galaxy counts don't come from direct observation at all. They come from statistical models. Astronomers observe a small patch of sky, count the galaxies they find there, measure their properties, and then extrapolate those numbers across the entire observable universe. This isn't bad science. It's necessary science given our limitations, but it means our total galaxy count of 2 trillion is essentially an educated guess based on sampling an almost invisibly small fraction of space. Think about what this means for our understanding of cosmic structure. When astronomers talk about galaxy evolution, about how galaxies form and grow and merge over billions of years, they're building theories based on studying 2.5 thousandths of 1% of the available examples. Every model of galaxy formation, every simulation of cosmic structure, every theory about how galaxies interact and evolve rests on that microscopically tiny foundation. Would you trust a medical study that examined 2.5 thousandths of 1% of patients and then made sweeping claims about all of humanity? Would you accept an election poll that surveyed the same fraction of voters? Yet this is the data foundation supporting much of modern cosmology, and there's something almost beautiful about that audacity, that willingness to peer into the darkness and try to understand it from just a few scattered points of light. The galaxies we have studied aren't representative. Large spiral galaxies like the Milky Way dominate our catalogues because they're bright and easy to see. Elliptical galaxies appear frequently in our surveys because they're often massive and luminous. But dwarf galaxies, which may actually be the most numerous type in the universe, are severely undercounted. They're small, faint, and difficult to detect unless they're relatively nearby. Some types of galaxies might exist that we've never seen at all. Galaxies that emit most of their light in infrared wavelengths we haven't thoroughly surveyed. Galaxies hidden behind dust clouds that absorb their visible light. Galaxies so diffuse and spread out that our instruments cannot distinguish them from background noise. Entire categories of cosmic structure might be missing from our current understanding simply because we haven't looked in the right way or in the right places. This isn't hypothetical speculation. It keeps happening. Every time we build a more sensitive telescope, every time we survey a new wavelength of light, every time we look deeper or with better resolution, we find things we didn't expect. Galaxies that formed earlier than our theories predicted. Structures larger than our models said were possible. Objects that shouldn't exist according to our understanding of physics. The universe doesn't care what our theories predict. It simply exists. Vast and complex and mostly unseen, waiting patiently for us to catch up. Our cosmic map is not incomplete. That word is far too gentle. Our cosmic map is barely started. We've sketched the rough outline of a few neighbourhoods while claiming to understand an entire planet. We've counted a handful of buildings and extrapolated the architecture of a civilization. We've seen a fragment and declared it representative of the whole. And yet from this absurdly limited data set, we've built sophisticated theories about dark matter, dark energy, cosmic inflation, and the ultimate fate of the universe. Either we're extraordinarily lucky that our tiny sample happens to be representative of the whole, or we're missing something fundamental. The answer should be obvious and deeply humbling. But there's no need to feel frustrated by this. The universe has been here for 13.8 billion years. It's not going anywhere. It can wait while we slowly, carefully, begin to understand why seeing so little is simply the nature of trying to observe something so impossibly vast. And that brings us to a question that seems obvious at first. That obvious question sounds something like this. If we've only studied a tiny fraction of galaxies, if most of the universe remains unseen, why not just point our telescopes everywhere and observe it all? Why not scan the entire sky, catalogue every galaxy, and finally build a complete map of the cosmos? It sounds simple enough. We have powerful telescopes, we have sophisticated instruments, we have the technology. So why haven't we done it? The answer reveals a problem so fundamental, so built into the nature of observation itself, that it changes everything you might think about astronomy. This isn't about money or time or willingness, though those matter too. This is about the brutal mathematical reality of trying to observe something as vast as the universe, with instruments as limited as telescopes. The full sky, the complete sphere of space visible from Earth in all directions, covers approximately 41,000 square degrees. That's the total area we could theoretically observe if we pointed telescopes in every direction and captured every photon of light arriving from every corner of the cosmos. 41,000 square degrees. That's our complete observational canvas, our entire workspace. Now, consider how telescopes actually work. They don't scan the sky like your eyes scanning a room. They stare at tiny patches of space, often for hours or days at a time, collecting light photon by photon. The smaller and fainter the object you want to see, the longer you must stare at it. Distance makes things faint, incredibly and impossibly faint. A distant galaxy might send only a handful of photons per second toward Earth. To detect it, to actually gather enough light to form an image and measure its properties, you need to point your telescope at that exact spot and wait. The Hubble Ultra Deep Field, one of the most famous astronomical images ever captured, shows this problem perfectly. That image covers a patch of sky so small it represents 1/13 millionth of the total sky. 1/13 millionth. You could fit that entire image inside the area covered by a grain of sand held at arm's length. It's almost invisibly tiny compared to the full sphere of observable space. To capture that single image, astronomers pointed Hubble at that one spot for hundreds of hours. They collected data over multiple observation sessions, carefully stacking exposures, filtering out noise, gathering every possible photon that arrived from that particular direction. The result was stunning. That tiny patch revealed thousands of galaxies, some so distant their light had travelled for over 13 billion years to reach us. It showed galaxies that formed when the universe was less than 1 billion years old, cosmic infants captured in a moment of ancient light. But here's the crushing reality, the quiet mathematics that governs all of observational astronomy. If you wanted to observe the entire sky with the same depth and sensitivity as the ultra-deep field, if you wanted to see every faint distant galaxy across the complete 41,000 square degrees of observable space, it would take approximately 300,000 years of continuous observation time. 300,000 years. Civilization has only existed for a few thousand years. Modern astronomy has only existed for a few centuries. Hubble itself has been in orbit for only 3 decades. You cannot observe the whole universe deeply. The mathematics simply doesn't work. You must choose. You can look deep, staring at tiny patches of sky for extended periods, seeing the most distant and faint objects. Or you can look wide, surveying large areas quickly, but only detecting bright nearby galaxies. You cannot do both. The universe is too vast and telescope time is too limited, too precious. Telescope time is one of the most valuable resources in astronomy. Only a handful of telescopes exist that can see deep into cosmic distance. Hubble, James Webb, the Very Large Telescope in Chile, a few others scattered across the planet. Thousands of astronomers compete for observing time on these instruments. Proposals are submitted, reviewed, ranked by scientific importance. Only a fraction of requested observations actually happen. Every hour of telescope time represents a choice, a decision about what to observe and what to leave unseen. This creates a fundamental trade-off that governs all observational astronomy: depth versus coverage, sensitivity versus area, detail versus completeness. The universe has been here for 13.8 billion years. It's not going anywhere. It can wait while we slowly, carefully, begin to understand why seeing so little is simply the nature of trying to observe something so impossibly vast. And that brings us to a question that seems obvious at first. That obvious question sounds something like this. If we've only studied a tiny fraction of galaxies, if most of the universe remains unseen, why not just point our telescopes everywhere and observe it all? Why not scan the entire sky, catalogue every galaxy, and finally build a complete map of the cosmos? It sounds simple enough. We have powerful telescopes, we have sophisticated instruments, we have the technology. So why haven't we done it? The answer reveals a problem so fundamental, so built into the nature of observation itself, that it changes everything you might think about astronomy. This isn't about money or time or willingness, though those matter too. This is about the brutal mathematical reality of trying to observe something as vast as the universe, with instruments as limited as telescopes. The full sky, the complete sphere of space visible from Earth in all directions, covers approximately 41,000 square degrees. That's the total area we could theoretically observe if we pointed telescopes in every direction and captured every photon of light arriving from every corner of the cosmos. 41,000 square degrees. That's our complete observational canvas, our entire workspace. Now, consider how telescopes actually work. They don't scan the sky like your eyes scanning a room. They stare at tiny patches of space, often for hours or days at a time, collecting light photon by photon. The smaller and fainter the object you want to see, the longer you must stare at it. Distance makes things faint, incredibly and impossibly faint. A distant galaxy might send only a handful of photons per second toward Earth. To detect it, to actually gather enough light to form an image and measure its properties, you need to point your telescope at that exact spot and wait. The Hubble Ultra Deep Field, one of the most famous astronomical images ever captured, shows this problem perfectly. That image covers a patch of sky so small it represents 1/13 millionth of the total sky. 1/13 millionth. You could fit that entire image inside the area, covered by a grain of sand held at arm's length. It's almost invisibly tiny compared to the full sphere of observable space. To capture that single image, astronomers pointed Hubble at that one spot for hundreds of hours. They collected data over multiple observation sessions, carefully stacking exposures, filtering out noise, gathering every possible photon that arrived from that particular direction. The result was stunning. That tiny patch revealed thousands of galaxies, some so distant their light had travelled for over 13 billion years to reach us. It showed galaxies that formed when the universe was less than 1 billion years old, cosmic infants captured in a moment of ancient light. But here's the crushing reality, the quiet mathematics that governs all of observational astronomy. If you wanted to observe the entire sky with the same depth and sensitivity as the Ultra Deep Field, if you wanted to see every faint distant galaxy across the complete 41,000 square degrees of observable space, it would take approximately 300,000 years of continuous observation time. 300,000 years! Civilization has only existed for a few thousand years. Modern astronomy has only existed for a few centuries. Hubble itself has been in orbit for only 3 decades. You cannot observe the whole universe deeply. The mathematics simply doesn't work. You must choose. You can look deep, staring at tiny patches of sky for extended periods, seeing the most distant and faint objects. Or you can look wide, surveying large areas quickly, but only detecting bright nearby galaxies. You cannot do both. The universe is too vast and telescope time is too limited, too precious. Telescope time is one of the most valuable resources in astronomy. Only a handful of telescopes exist that can see deep into cosmic distance. Hubble, James Webb, the Very Large Telescope in Chile, a few others scattered across the planet. Thousands of astronomers compete for observing time on these instruments. Proposals are submitted, reviewed, ranked by scientific importance. Only a fraction of requested observations actually happen. Every hour of telescope time represents a choice, a decision about what to observe and what to leave unseen. This creates a fundamental trade-off that governs all observational astronomy: depth versus coverage, sensitivity versus area, detail versus completeness. You can spend weeks observing a single galaxy in exquisite detail, measuring its rotation, its chemical composition, the age of its stars, the presence of a central black hole. Or you can spend that same time surveying thousands of galaxies, cataloguing their positions and rough properties, but learning little about any individual object. Both approaches are valuable, both are necessary, but both leave vast gaps in our knowledge. The detailed observations tell us about specific objects but provide no sense of how common or rare those objects might be. The wide surveys give us statistics and numbers but lack the depth to understand what we're actually looking at. We're trying to build a complete picture of the universe by combining these incomplete views, like assembling a jigsaw puzzle when most of the pieces are missing, and you're not even sure what the final image should look like. Every major telescope has a field of view, a specific area of sky it can observe at one time. Large field of view means you can survey more area quickly, but you sacrifice the ability to see fine details. Small field of view means incredible detail and sensitivity, but you can only observe tiny patches at a time. There's no perfect instrument. Every telescope is a compromise between competing priorities. James Webb Space Telescope, the most powerful observatory ever built, faces the same constraints. It can see farther and fainter than any previous instrument. It observes in infrared wavelengths that reveal the most distant galaxies in the universe. But its field of view is relatively small. To survey even a modest fraction of the sky with Webb would require centuries of observation time. So astronomers carefully select their targets, focusing on the most scientifically valuable regions, knowing that most of the sky will remain unobserved at Webb's sensitivity level. This isn't failure, this is reality. The universe is simply too large, too complex, too filled with structure at every scale to observe completely. We're forced to sample, to extrapolate, to build statistical models based on limited data. And every time we do this, we introduce uncertainty. We create blind spots. We miss things that might be fundamentally important but happen to exist in regions we haven't observed. So we stand here now with our powerful instruments and sophisticated techniques, having observed less than 0.003% of all galaxies, trying to answer fundamental questions about the nature of reality itself. We're working with incomplete data, biased samples, statistical extrapolations that might or might not reflect the true universe, and the invisible universe simply waits, vast and patient and utterly indifferent to our limitations. It has no deadline, it rushes for no one. But even when we do point our telescopes at something, even when we successfully capture its light, something else complicates the picture. That complication is written into the fabric of space-time itself. There are galaxies out there, billions upon billions of them, that aren't invisible because we haven't looked. They're invisible because the universe itself has made them impossible to see with certain types of telescopes. This isn't about technology or time or resources. This is about physics, about the way reality works at its most fundamental level. The universe is expanding, not just drifting apart, but actively expanding. The space between galaxies is stretching, growing larger with every passing moment. This isn't controversial or speculative. It's one of the most well-established facts in cosmology, confirmed by decades of observations. But expansion does something strange to light, something that fundamentally changes what we can and cannot observe. When light travels through expanding space, it gets stretched along with that space. Imagine drawing a wave on a rubber band and then pulling the rubber band apart. The wave gets longer, its wavelength increases. Light behaves the same way. As photons journey across billions of light years of expanding cosmic space, their wavelengths stretch. They shift toward the red end of the electromagnetic spectrum. This phenomenon is called redshift, and it's both beautiful and frustrating in equal measure. For nearby galaxies, redshift is minimal. Light shifts only slightly. A galaxy a few million light years away shows barely any redshift at all. Its light looks almost the same as when it was emitted, but as distance increases, redshift becomes dramatic. A galaxy 5 billion light years away has its light stretched significantly. A galaxy 10 billion light years away shows extreme redshift. And galaxies at the edge of the observable universe, whose light has been travelling for over 13 billion years, experience redshift so severe that it completely transforms the nature of their light. Here's what that means in practical terms, and most galaxies and deep images have only estimated redshifts based on rough brightness measurements, which means their distances carry large uncertainties. You might think you're looking at a galaxy 12 billion light years away when it's actually 10 billion light years away. That error changes everything about your interpretation of its properties. Distance and redshift together create a conspiracy of invisibility. The universe stretches light across billions of years. It weakens photons. It transforms wavelengths. It makes the distant universe fundamentally different from the nearby universe, not just in appearance, but in the very nature of the light we receive. And all of this happens simply because space itself is expanding, pulling everything apart, stretching the fabric of reality as time flows forward. The universe isn't hiding from us maliciously. It's just doing what universes do. expanding, evolving, existing across scales of time and space that make observation almost impossibly difficult. But almost impossible isn't the same as impossible, and that brings us to what happens when we finally do manage to see. What happens when we finally do manage to see into that darkness is both humbling and extraordinary. The invisible universe isn't just more of the same, it's not simply additional copies of what we already know. Every time we've gained the ability to see deeper, to look farther, to observe in new wavelengths, the universe has surprised us. It has shown us things we didn't predict, structures we didn't expect, galaxies that challenge everything we thought we understood. James Webb Space Telescope, with its unprecedented infrared vision, has been opening our eyes in ways we're only beginning to comprehend. In its first year of deep observations, Webb revealed something startling. In one particular survey, astronomers found over 1,700 galaxy groups in the early universe, cosmic neighborhoods that existed when the universe was less than 1 billion years old. 1,700 structures where galaxies were already clustering together, already forming the kinds of cosmic cities we see in the present-day universe. This shouldn't have been possible according to some of our models. The early universe was supposed to be simpler, more uniform, still in the process of organizing itself into the complex web of structure we see today. But these galaxy groups were already there, already gravitationally bound, already evolving. The universe, it seems, became organized faster than we thought. It wasted no time in building complexity. And then there's the Big Ring, a structure so large it challenges our understanding of how the universe can organize itself. A ring-like arrangement of galaxies spanning roughly 1.3 billion light-years across. Structures this large aren't supposed to form easily. The physics of gravity, working slowly over billions of years, should limit how big coherent structures can grow. Yet there it is, vast and real, a cosmic architecture that suggests the universe has ways of organizing itself that we haven't fully understood. These discoveries aren't anomalies or mistakes. They're glimpses of what exists in the invisible majority of the universe we haven't yet observed. Every deep field image reveals unexpected things. Every new wavelength we survey shows us galaxies we couldn't see before. Every improvement in sensitivity brings previously invisible structures into view. The pattern is clear. The universe we haven't seen is different from what we expected. Not wildly, incomprehensibly different, but different enough to keep reshaping our theories. Different enough to keep teaching us humility. Future telescopes are coming. The Vera Rubin Observatory will survey the entire visible sky repeatedly, creating a time-lapse movie of the universe, capturing transient events and distant galaxies with unprecedented efficiency. The Nancy Grace Roman Space Telescope will have a field of view 100 times larger than Hubble's, allowing it to survey vast areas of sky while maintaining exquisite sensitivity. These instruments won't solve every mystery. They won't observe every galaxy, but they'll dramatically expand the fraction of the universe we can study, from thousandths of a percent to perhaps a few percent. Artificial intelligence is helping too, not replacing astronomers but amplifying their capabilities. Machine learning algorithms can now scan through millions of galaxy images, identifying unusual structures, classating types, detecting faint patterns that human eyes might miss. They can predict which galaxies are worth detailed study, which regions of sky might harbour rare objects, how to optimise telescope time for maximum scientific return. The combination of new instruments and intelligent analysis is slowly, steadily pushing back the boundaries of the invisible. But even with all these advances, we must remember something fundamental. The universe is patient. It has existed for 13.8 billion years. It will exist for trillions more. Our current ignorance is temporary, but our limitations are real. We'll never observe every galaxy in detail. We'll never capture every photon of light. We'll never fully eliminate the gap between what exists and what we can study. The invisible universe will always be larger than the observed universe, and perhaps that's as it should be. Perhaps there's something right about living in a cosmos that remains mostly mysterious, mostly unexplored, mostly waiting to be discovered. We stand at a particular moment in history where we know we're mostly blind but are slowly gaining sight. We can measure our ignorance, calculate it, understand its dimensions. That awareness itself is a kind of progress, a kind of wisdom. The 9,000 stars you can see on a perfect night are still there, still beautiful, still worth contemplating. They haven't changed. What has changed is your understanding of what they represent. Those points of light are no longer the universe. They're a sample, an impossibly tiny glimpse of something far vaster. The darkness between them is no longer empty. It's full, packed with galaxies and stars and structures beyond counting, most of which you'll never see, many of which humanity will never catalogue. But the universe doesn't mind. It's not offended by your limitations. It simply exists, vast and patient and real, whether you observe it or not. The invisible galaxies continue forming stars. The unobserved structures continue evolving. The light that hasn't reached us yet continues its journey across expanding space, travelling for billions of years toward a future observation, toward a telescope that might not even be built yet, toward eyes that might not yet be born. And you can rest now, knowing that the cosmos will still be there when you wake. It's not going anywhere. The galaxies can wait, the darkness can wait, the questions can wait. Everything we've talked about, everything that exists out there in that vast invisible universe, has been waiting for billions of years already. It can wait a little longer while you drift off, while you rest, while you let these thoughts settle like cosmic dust slowly falling through the darkness of space, gathering gradually, patiently over time scales that make human urgency seem absurd. The universe knows how to wait, and now so do you. Sleep well. The stars will still be there in the morning, all 9,000 of them that you can see, and all the billions of trillions more that you cannot.